Hey Chem students, Ben Azmon here. Today we're going to be diving into our very first organic reaction, acid-catalyzed dehydration. Let's get to it. Acid-catalyzed dehydration. It's a phenomenal early reaction that turns an alcohol into alkene. Our alcohol is 2-methylcyclohexanol. As for what alkenes it turns into, we're going to let you figure that out. But I'm going to give you at least a little bit of a hint. Our mechanism starts off with our alcohol picking up an H+ from phosphoric acid. This is followed by water leaving, giving us a carbocation intermediate. Now we use phosphoric acid because it's a strong non-nucleophilic acid. If we use the nucleophilic acid like HCl or HBr, we'd end up with something very different. Now from here we have a few different pathways which end up with 3 different products, one of them having an additional intermediate. That additional intermediate is going to require a hydride shift. Now a hydride is just a hydrogen with a lone pair, and a hydride shift occurs anytime you have a primary or secondary carbocation next to a tertiary hydrogen. So the hydrogen with its electrons from the bond will jump to the less substituted carbocation, creating a more stable, more substituted carbocation. The final hint I'll give you has to do with alkene stability. In general, the more substituted, the more stable an alkene will be. The less substituted, the less stable. Now according to Zaitsev here in his rule, the most stable alkene will be the major product. As this is the first time we're using one, you're going to need to know a few things about catalysts. 1, it speeds up a reaction. Next, it goes through a different pathway. If this is the normal uncatalyzed pathway, this might be the catalyzed one. Last 2 things, you get it back at the end of the mechanisms, which means it gets reused, and despite being the smallest number of moles, will never be the limiting reactant. So for today's reaction, we have to achieve quite a high temperature, so we have to start heating up now. Now I'm going to start off by taking one of the 2 thermometer adapters. We need one so we can firmly hold it in place without sliding too deep into the sand bath and giving us a false reading. We're going to start off by clamping it as firm as we can, attaching it way too high so we can adjust any angles we need to, and then lowering it into the sand bath. We want to just be able to see the little blue triangle above the level of the sand. Plug it in and start heating immediately. The exact setting is going to depend a lot on your hot plate, but we want to keep it ideally somewhere between 180 and 190. But keep an eye on it, you're going to have to keep fiddling with it. To measure out your alcohol, you're going to need a 5 ml conical vial, tared, and one of these pipettes. They should be out on the workstation. I know it's a little strange measuring a liquid by weight, but we want the extra precision of the scale. Just get it somewhere in the ballpark and write down how much you took. So we're going to want to heat and stir it at the same time. We have 2 options for this, a stir bar and a spin vane. For this, the stir bar obviously is not going to work, so let's take the spin vane. To ensure that it's going to stir properly, make sure that it's facing point down. To measure out our acid, you can either use a graduated pipette, or far easier is you can just count out 14 drops. That will approximate the 0.7 mils, and remember, we don't need extra precision for this because catalysts get regenerated. Now we're going to directly distill our product off, so we'll need a Hickman still, a cap with a hole, and an O-ring. Make sure you put them on in this order and that you get them both past the lip, otherwise it won't close tight enough. Lock it in place. Now this time we're going to clamp it at the top piece. We can do this because we tightly connected the 2 together, and we also need to get this vial really deep in the sand bath. Make sure your spin vane is centered perfectly forward, back, left, right, otherwise it won't spin that fast. If it doesn't spin that fast, you don't get even heat distribution, and this will take longer. I recommend shoring up the sand on the vial to increase contact. Remember, one of the easiest ways to tell how far up our distillate has made it is literally by touching the glass and seeing where it's warm. This takes longer than you would think, at least half an hour, but be patient. It also helps to come down to this angle to see the distillate accumulating in the Hickman. Sometimes it's hard to see from the top. Next you're going to need a vial. No, not that one, the big one, the 10 ml vial. And you'll need a 9-inch pipette. They'll be out on the bench top somewhere. Bring your vial close just in case it drips so you don't lose anything. Slip your pipette in at a sideways angle and collect some of your sample. Now you're not going to get everything at once, so make sure you cap your vial between recoveries. Now don't worry if your solution becomes a little hazy. That's just the water interacting with our product, which is far less polar than our starting material. If collection slows down or if it's really taking a long time, you can take a piece of foil and fold it over itself multiple times so it's nice and thick, and then rip a line through it, dig out a little hole, then slip it over the vial, making sure that the cap isn't covered because it will melt, pressing it down so it covers the sand bath, and making sure it doesn't touch the thermometer. Eventually collection is going to slow down. You're going to have to remove the foil and check if there's anything left. If it's like this, a little bit of thick yellowish oil at the bottom, you're done. Now we're going to want to neutralize that acid and remove the water. To do that, we're going to use some sodium carbonate. Now the exact amount you need is going to be different from time to time, from student to student. What you're going to do is you're going to add some, shake it up, and look for these 3 criteria. First, there's no visible water droplets either floating or sunk to the bottom of the solution. Next, it should look clear, not cloudy or hazy. And finally, some, but not all of the drying agent should be loose, looking like it did in the bottle. Because if those grains didn't clump, they didn't find water. Next, you're going to want to pre-weigh one of the 6 or 4 ml little vials. Next, you're going to want to take that vial and pipette out your product while leaving the drying agent behind. If you did catch any of the drying agent, you can always manually remove it using your spatula. Next, we're going to want to weigh our product because we're going to need some of it to do a test. For this, we'll need a second vial. You can label them. I'm using 2 different colored caps. You can add 1 or 2 drops of your weighed product. And then using about a ml of diethyl ether, we're going to dilute that. It's about 1 pipette full. It's close enough. Now the test we're going to run is called GC, or gas chromatography. Much like column chromatography, it has a stationary and mobile phase. But the stationary for this one is a bound liquid, and the mobile phase is a gas. Now this is a stupendously simplified version of what gas chromatography is. You have a gas tank, usually with nitrogen or argon. You have a syringe to load your sample into an injector, and the injector injects your solution onto the column, which is in a heated oven. The carrier gas then pushes it down this very long column. Normally this would separate based off polarity, but considering our products are all basically the same polarity, it's going to separate more on boiling point differences. Once it passes through the column, it goes to a detector, and the detector and a few other components turn this into a signal the computer can understand. You're expecting 3 peaks, 1 peak per product. You can determine which peak is which product using Zeitzet's rule or their boiling points. You can use the area under each curve to determine the percent you made of each product. This is our GC. You can see it has a very thin, very long column. It has some ejector ports and the computer. Okay, to prep your sample, you first need to clean out the syringe. God knows what other people have done with it before. We're going to use a little bit of the same solvent, diethyl ether, make our lives easier. This is a 10 microliter syringe. It's quite delicate, so you want to treat it with respect. To clean it, you just suck up some ether and then shoot it out. Repeat 3 or 4 times. Now you're going to need 1 microliter. To do this, you first want to suck up a little bit of air, about 2 microliters, then 1 microliter of your dilute sample, and then another 2 microliters of air. In the end, it should look something like this. Air solution air. To run the GC, hit prep run. Check to see if the machine's ready. You never want to stick it in before it's ready. Place the tip of the needle in the center of the injector and use your fingers to help guide the syringe in. You don't want to bend the needle. Depress the plunger and immediately pull out. Once the machine is ready, click start. 2 to 3 minutes later, you print it out and you're done.